Hello friends, welcome to the channel. This is the third video in the series of Staad Pro, where we are calculating dead load, live load and wind load, and further we will apply it on the given truss and we will analyze it in Staad Pro. So we have already seen how to apply dead load and live load in our first two videos, and also we have seen how to calculate the tension and compression values in any of the member in the given truss. So in this context, today we are going to learn how to calculate wind load from IS 875 Part 3 2015. So we will go step by step and I hope that you will get my points. Okay, so let us move to our problem statement. So as you can see, this is our problem, that is design and analyze this truss for wind forces. We are going to calculate how we will apply this wind force on this given truss. So ignore the rest of these members. We have to only apply the wind load on this particular face of the truss, as you can see in the picture. I have given dimensions of this truss members, of rafter and all other members in this figure. You can select your dimensions suitably and then further calculate. As you can see here, the angle of truss is 18 degree, and these all members or rafter are of equal lengths, and this height is 7 meter, and the spacing between two frames is 5.5 meter. So please draw this picture on any rough copy or keep it in mind. So moving to the next slide. Okay, so first of all, we should know how the direction of wind load is applied on the truss. As we have earlier seen that gravity loads, that is dead load and live load, acts perpendicular uh, to x-axis, that is in vertical direction, whereas this wind load acts perpendicular to the rafter at nodes. You can see the direction marked by red arrows. So this is the direction of action of wind loads. So we will keep this in mind, and we have to calculate this value of these vectors. And further, after calculating value of these vectors, we will divide it into x component and y component and further apply in the Staad Pro. Okay, so let us see how we will do it step by step. So moving to the next slide, this is our roadmap. This is the roadmap to calculate the wind load from IS code. So first of all, we have to calculate basic wind speed, that is VB. Then we will get design wind speed Vz, then we will get wind pressure Pz, then we will go for design wind pressure Pd. Then after that we have to calculate pressure coefficient. This is the critical part of the wind load calculation, so please be careful at this point. And then further we have to move to calculate wind force on each node, that is F. And finally we have to apply this F in the Staad Pro by breaking into X component and Y components. So let us see step by step. Okay, so to calculate wind speed, that is VB, refer Annexure A, page 51. Here, first of all, find the city in which your roof truss or structure is being built. So my structure is being built in Roorkee, and already here it is given basic wind speed is 39 meter per second. So my VB value will be 39 meter per second, and you get accordingly. Moving to the next slide, our second component was VZ. So VZ can be calculated from 6.3 design wind speed VZ. Okay, so what are the factors you have to keep in mind is that first of all we have to get K1, K2, K3, K4. VB we have already got. So to get K1, K2, K3 and K4, they are actually risk coefficient. Second is K2 is terrain roughness, K3 is topography factor, and K4 is importance factor. You can read about them in detail from this slide or from IS code itself. So risk coefficient, that is K1, is basically seen from this table, that is table 1, clause 6.3.1. Okay, I am assuming that our structure lies in the category of all general building and structures. Okay, then for this wind speed, 39, which I have already got in the first slide, the given value of K1 is 1. So I got the K1 value. You can select your K1 value from this table itself. Okay, now moving to the K2 value, that is terrain roughness. Okay, so to get K2 value from here at terrain height factor, K2 factor, in this, as you can read, there are four categories: category 1, category 2, category 3, and category 4. Here I have not shown. So basically, it tells that what is the height of your building and the density of buildings in your area, according to which we have to select this K2 factor. Okay, so my building lies in category 2, that is open terrain with well scattered obstruction, having heights generally between 1.5 meter and 10 meter. You can search on internet also, and you will easily get the K2 factor by directly putting the city in which you are going for construction. So for category 2, the value of K2 is here in this slide. Table 2, factors obtained design with speed variation with height in different terrains. Here it is given the value of K2 for terrain category 2 and height. Height is less than 10 meter. As you can remember, I have already shown the height of my structure is 7 meter. Okay. So for height less than 10 meters, the value of terrain category 2 is 1. Okay. So I hope you got this table and you can select the value of K2 as per your requirements. Now moving to the third factor, that is K3. So K3 basically depends on the topography, and here you can read the highlighted lines. That is, the effect of topography shall be significant at a site when the upwind slope is more than about 3 degrees. Okay, so I am assuming that the slope angle is less than 3 degree for my case, and you can assume it too. But if you want more precise value, you can refer annexure C. And in the annexure C, there has been given a procedure to calculate the topography factor, that is K3 factor. Okay, if the theta value is less than 3, we can simply assume K3 is equals to 1. And if you are getting theta, that is upwind slope, more than 3 degree, then you have to calculate the value of K3. Okay, so I got K1, K2, K3, and let's move to get K4. Okay, so K4 is basically importance factor for cyclonic region. If the structure lies within 60 kilometer of the coastline, okay, then you have to put the value of K4 as 1.30. Okay, or if the structure is lying outside of 60 kilometer, then for industrial structure we have to put 1.15, and if it is not an industrial structure or simple structure, then we have to take value of K4 as 1.00. Okay, so in my case, since it is industrial structure, so I am taking it as K4 is equals to 1.15. So now we have got all along the way K1, K2, and K3, K4 values. So here, as you can see, K1 is equals to 1, K2 is equals to 1, K3 is equals to 1, and K4 is equals to 1.15. So substituting all these value in the equation, Vz is equals to K1, K2, K3, K4, Vb, I got Vz value 47.28. Okay, that is design wind speed. And if you can remember, after design wind speed, we have to calculate designed wind pressure from the first slide. It is better if you note down the steps. I am again moving to the roadmap. So this is the roadmap. You can pause the video and note down the step. It will be helpful. So moving to the slide. Okay. So how to calculate PZ? So basically PZ is 0.6 VZ square, as you can see here in this formula. So we just simply have to put the value of Vz and square it and multiply by 0.6 to get PZ. Since PZ is pressure, so value is Newton per meter square. After PZ, we have to go for PD, that is design pressure. For design pressure, there are three coefficients, KD, KA, and KC. we have to compute this coefficient from the table, and further we have to multiply it from PZ to get PD. So basically KD is wind directionality factor, Ka is area averaging factor, and Kc is combination factor. Let us see one by one how to get it. Okay, so first coming to wind directionality factor, that is KD. So as you can see here, it is given building solid science, open science, lattice framework, uh, and all triangular, square, rectangular, and factor of 0.90 may be used on the design wind pressure. So basically you can read this entire paragraph and you can conclude that if the building type is these all square, rectangular, you have to use 0.90 as KD, and if circular or near circular forms, we have to use 1. So since our uh, frame is triangular, so we will use KD as 0.9. So from this table we can get KD as 0.9. Further moving to area averaging factor, that is Ka. This is important. Okay, so what is area averaging factor? To calculate area averaging factor, first of all, let me move to the next slide. Okay, so as you can see, this is the structure, and tributary area is given by spacing between frame. This is spacing between frame. This is first frame, this is second frame, and the spacing between frame is 5.5 in my case, and multiplied by rise of frame. This is the rise of frame. Okay, so in my case, rise of the frame is 2.44 meter. This is the rise, 2.44 meter. So upon multiplying this spacing between the frame and rise, we can easily get the tributary area. Okay, and from this table, if you are getting tributary area less than 10 meter square, then put area averaging factor, that is Ka as 1, and otherwise if you are getting tributary area in between these two area, you can linearly interpolate to get the value of Ka. Okay, and you can also read this paragraph to get more about Ka. So moving to the next factor, that is Kc. Okay, so for Kc, we are referring 7.3.3.13 clause, and here it is directly written that Kc value is 0.90. Okay, so we got Kd, Ka, Kc, and we have already calculated Pz. So putting all these values, we can easily calculate Pd, that is design wind pressure, and it is 1064.67 Newton per meter square. Now, our next step will be to calculate the pressure coefficient. This is the most crucial part of wind calculation. So please be patient and listen carefully. Okay, so what is pressure coefficient? Basically, pressure coefficient will be further used to calculate the force on each node, which was our final key element in the roadmap. Let me show you again. Okay, as you can see, after calculating pressure coefficient, we have to calculate wind force on each node. So this pressure coefficient values will be required in the formula of calculation of wind force on each node. Okay, so let us see how to calculate pressure coefficient. If you have any doubt or you need any more clarification, you can simply open the IS code and can get everything you want. Okay, so pressure coefficient is basically written as Cp, and value of Cp is Cp external minus Cp internal. Cp external means external pressure coefficient, Cp internal is internal pressure coefficient. Okay, um, from clause 7.3.2.1 or 2.2, which is given in IS code, we can get that Cp internal value is plus minus 0.2 if the opening area is less than 5%. Opening area means the area from where the truss structure opens, that is from doors, windows, or any other opening which is provided in our structure. If the area is less than 5%, then you have to take CP internal as plus 0.2 and minus 0.2. And if the opening area is large, that is area lies between 5% to 20%, then we have to take CP internal as plus or minus 0.5. So I am assuming that uh, my opening area lies between 5% to 20%, then CP internal will be plus minus 0.5. So among these two variables, I got CP internal values. But for CP external values, we have to refer a table given in IS code from where we can calculate CP external. Let me show that table to you. Okay, so this is the table. This is clause 7.3.3.2, external pressure coefficient CPE for pitched roof. Okay, so here, first of all, you have to calculate H by W. H is the height and W is the width. Okay, so let me show you the picture again. As you can see here, height is 7 meter and width is 15 meter. So that is H by W. Okay, so if H by W is less than or equal to 0.5, then you have to take the case number 1. Otherwise, if H by W lies between 0.5 to 1.5, you have to take case 2. So as per your data, you can select among all these three cases. This is the step number 1. Okay. Then step number 2 is to calculate the or to get the roof angle from your uh, problem statement. So since my roof angle is 18 degree, so my values will lie between 10 to 20 degree. I am assuming 20 degree for simplicity. You can go for linear interpolation for more accuracy. Okay, so there are a few points which you need to get it before going for the calculation of CP external. Okay, so there are basically 4 cases how wind can move and can affect the given truss. Okay, so suppose this is the entire truss structure and this is our baseline. This is horizontal baseline and wind is moving at theta is equals to 0 degree. That is, and it means that wind is moving along this baseline. And if theta is 90 degree, this means angle is 90 degree from the baseline. That is, wind is moving from this direction to uh, this direction. Okay. So in technical terms, the side which is facing the wind, it is called windward direction, and the side which is opposite to the direction of the wind, that is called leeward direction. And if wind has been flowing in this direction, then this will be the windward direction and this will be the leeward direction. Okay, why I am telling you? Because as per windward or leeward direction, we will be getting different values of CP external from the table. So we got ultimately 4 parameters, that is theta 0, theta 90 and windward leeward direction. So using these 4 parameters, we are going to make table for windward and leeward direction. If theta is 0 degree and CP internal is plus 5, theta is 0 degree, CP internal is minus 0.5, theta is 90 degree, CP internal plus 0.5, theta is 90 degree, CP internal minus 0.5. These all are the variables and corresponding to these variables, we have to calculate value of CP net in windward direction and in leeward direction. So if you can see from this table, this is the baseline and this direction is windward direction, that is EF is the windward direction for theta is equals to 0 degree. Okay, so in my case, if theta is 0 degree and windward direction is EF, the value of CP external is minus 0.4, and for leeward direction, that is GH, value of CP external is again minus 0.4. So how to put that? Here I have shown Cp external is minus 0.4 for windward and Cp external is minus 0.4 for leeward. And Cp net is Cp external minus Cp internal. Cp internal plus 0.5. So you can simply calculate minus 0.4 minus 0.5. That is Cp net is minus 0.59 for both the cases. Similarly, for the second case, here theta is 0 degree and Cp external is minus 0.4, which is same as this, because theta is 0 degree means the side is same. Windward and leeward side are same. So the coefficients from the table are same. And you can calculate Cp net. But for theta 90 degree, again moving to the table, this is given here, wind angle 90 degree. If wind angle is 90 degree, then wind is approaching either from this side or this side. So assuming that wind is approaching from this side, the windward direction is Eg and leeward direction is Fh. So for Eg value, the Cp net value, Cp external value is minus 0.7. And for leeward direction, that is Fh direction, the Cp external value is minus 0.6. So let me use it in the table. So here, as you can see, Cp external value is minus 0.7 for theta 90 degree and Cp external value is minus 0.6 for leeward direction. And it will be same in the case of theta 90, Cp internal value is minus 0.5. So from this table, you can calculate total 8 cases for Cp external. And for these 8 cases, we are going to get 8 values of forces. So value of force can be calculated as per clause 7.3.1, wind load on individual members. Here you can see a simple formula, that is F equal to Cp into A into Pd. Cp is Cp external minus Cp internal. Okay, so you have to multiply by area and design wind pressure. What is the area here? Area is spacing into distance between purlins. Spacing, this is the spacing between two truss and this is the distance between purlins. Okay, so you have to multiply this value 5.5 into 1.97 for my case, and it comes out to be 10.83 meter square. So you got A, you got PD, you got CP. Now you can calculate F for all the 8 cases separately. Let me show you to you. Okay, so here I have calculated force for all the 8 cases. It is simple because Cp external value is minus 0.9 for first case, minus 0.9 for first case, and then 0.1 for second case, and similarly. So in this manner, we can get the value of force. Please be careful about sign, because sign indicates whether the force is acting away from the truss or towards the truss. If sign is negative, it means the force is acting away from the roof of the truss, means it is acting inside out. And if the value of force is positive, that is, it means that force is acting towards the truss. Okay, so I have indicated for your convenience. In this manner, we have calculated the values of forces which will be acting on either side of the truss. Now, our final task is to uh, break down each forces vector into components. So, as you can see in the first case, the value of force is 10.38 on the left truss and 10.38 on the right side of the truss. So here I simply broke it down into the horizontal and vertical components. Because in the Staad, it is easy to apply horizontal and vertical components. Um, since it has option available for X and Y direction. And it will be quite difficult to apply 10.38 at a certain angle. So simply break down this value of force in both the direction, and now we will be seeing in the next video how to apply it on the nodes. Okay, so I hope that in this manner you can calculate the value of force and you have reached up to this point. Okay, thank you very much.